So I will unmute myself and I will let you know if someone asks question.
All right, thanks. Well, then it looks like we have the live stream going, so everything should be good.
Yes.
All right, thanks. And then for those of you just coming in, we'll just wait a couple more minutes or until 2 to start. But if you want to look at the problems that we're going to do today, you can go to, in the discussion, you can go to the course modules under week 1 and under discussion 1, and then there'll be the download link. So if you're on like a tablet and you want to write along in the slides, then there's the PDF there that has all of the problems that we'll be going over. Yes, yeah, they are the pre-lecture slides. Yeah, they just kind of call it like the pre-lecture slides, and then the post-lecture slides are going to be everything that I write up on these slides today, and I'll post the slides with my scribbles on them after the discussion today. And yeah, looks like everything is streaming correctly, and it's a new named stream, so. And we'll just go ahead and wait another minute, just as some people start to finish rolling in, and then we'll get started. Cool. So let's go ahead and get started. So this is our first discussion session. I'll just do a quick couple of reminders. So yeah, just make sure that you're muted. And then if you want to ask questions during the Zoom meeting, you can either just raise your hand or type in the chat. And then Lynn is the other TA here, and they'll be monitoring chat for any of the questions that you have there. And then the other just quick reminders just to be an active participant. So we're going to be doing lots of example problems. So make sure you're working on them kind of as we're going through them. I'm just going to give you a lot more practice, especially for homeworks or quizzes, because these are going to be very similar to those types of problems. So make sure that you're working along, and then just ask questions along the way as we go. And I'll ask for a couple of volunteers to either explain their solution or type their solution in the chat. So let's go ahead to our first problem. So here we've got a problem on number sequences. So we've got this sequence that starts with a sub 1 just being the letter A. And then we've kind of got this recursive formula here. So if n is even, then we're going to go to this case that a sub n is a sub n divided by 2b. And if n is odd, then we're going to go a sub n is equal to a sub n minus 1 divided by 2a. So we've got this recursive formula here with two different cases, depending on if n is even or n is odd. So just as an example, we can see that if we had a sub 2, we would go to the even case because 2 is even. Then we'd get a sub 2 divided by 2, b. And then a sub 2 divided by 2 is just a sub 1. We were given what a sub 1 was, so that would give us AB. And then if we did A5 as another example, we would go to the odd case because 5 is odd. So we'd have A sub 5 minus 1 divided by 2. 5 minus 1 divided by 2 is just 4. or 5 minus 1 is 4, divided by 2 is 2. So then we'd have a sub 2a. We solved what a sub 2 was here. It was just ab. So we'd end up with aba. So for the first problem, we want to write down what the first 10 strings in the sequence are. So by that, we mean what a sub 1 is, a sub 2, a sub 3, all the way up to a sub n. So if you want to just go ahead and take just a couple minutes on your own to try to work through what the first 10 strings in the sequence are, and then we'll go over it. And then if you have any questions, feel free to post them in the chat or raise your hand.
Here.
Okay, so we'll go ahead and just briefly go over this one. It's okay if you're still working. So just for part A, so we've got to write down the first 10 strings in the sequence. So we were given A1. It was A, on the previous slide, we solved what A2 was. And then we had what A5 was on the previous slide as an example. So does somebody want to either type in chat or just raise your hand for what A3 and A4 are? So it looks like we've got some in chat, and then Cameron, you can go ahead.
Oh, I can. I'm not a co-host, so I cannot unmute the student.
Oh, let me.
Yeah.
But I think Cameron, I think you can unmute yourself as well.
Yeah, I got it.
Okay.
So for A3, I got a squared because you take the odd equation, I guess, and get a of 3 minus 1 over 2, which would be a of 1 times a. So you'd get a squared.
Yeah. And so here we're just going to actually write just AA.
Oh, okay.
Just because we're representing these as kind of strings.
Okay.
So rather than these having some sort of like a being like a variable that you square some kind of number, we're just going to kind of represent them just with strings. And then, yeah, it looks like we had similar results in chat. Yeah. So if we had A4, we'd do A4 divided by 2b, which would be A1, or yeah, or A2b, and then ABB. And that's what people had in chat. And then does somebody else, either just by raising your hand or typing in chat, what A6, A7, A8, A9, and A10 are?
I can share those ones. So starting with A6, it's AAB, then it's AAA, then it's ABBB, then it's ABBA, and then last A10 is ABAB.
And then for 9, what'd you say you had?
ABBA.
And then 10, yeah, AB. Yeah, it looks like we've got a lot of people in chat agreeing with those as well. Yeah, so just for each of those, just plugging in the formulas here, and then just using whatever previous values we had to kind of get those later ones. Did anyone have any questions on finding any of these A6 through A10? Any questions on that?
It seems no question.
Cool. So let's go ahead to part B. So here we're going to use the results that we previously derived to determine what A17 are, and then what A21 is. And then just in case you need them again, I'll just finding A17 and A21, and I'll go ahead back to the previous slide just in case you missed. Anybody missed writing down a couple of those? Because you'll need them just for this next problem. So just take a minute and work through those two. Okay, so it looks like got some people who are done there. So does somebody want to either in chat or raise their hand, explain how they got A17, A21? So it looks like Dane, you raised your hand. You can go ahead.
I have asked him to unmute himself, but no response.
Okay, yeah, it's just the, yeah, if you just want to go ahead and unmute yourself, or if you can't, oh yeah, there you go.
Sweet. Yeah, so I took 17, since it's odd, subtract 1 divided by 2 brings you to A sub 8. A sub 8 is A, B, 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 and since it's odd, you have to add A to it. So I got A, B, 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 A.
Perfect. And then similar thing for A21. And then here we had A10, and A10 was A, B, A, B. And looks like, yeah, we've got some people agreeing in chat as well. So any questions on how we got either of those with A17 or A21? No, it looks good. Okay, so let's go ahead to the last part C of this problem. So here we suppose that we already know what A315 is, and then we need to find the values for A630 and A631. So just take a minute and go through how we'd find those two. Cool. So does someone want to go ahead and say kind of what they had for those two answers?
Dan has answered in the chat.
Oh yeah, we got some people. Yeah. So yeah, we do just add a B for the even one and A for the odd. Yeah, good observation there. But yeah, we can go ahead and yeah, just derive it too. So 630 divided by 2, B, which is A315, B. So yeah, we just add a B at the end here because we already know what A315 is. And then if it was A631, you just follow the formula. And then that'll be A315 just with an A on it. Just like that. And yeah, it looks like, yeah, Parker, you had it right too. So any final questions on this last problem here? No, looks pretty good. Cool. So let's go ahead to the second problem. So here we're given the following sequence. We've got 3, 6, 9, 12, 15. And then we're going to find either the next number in the sequence and then give the closed form and recursive form. So you just want to type in chat what would be the next number in the sequence. Yeah, that's good. Looks like lots of 18s. So that's good. So yeah, we can just see that for this sequence here, we're just going up by 3 each time. We're just adding 3 from the previous term. So if you want to go ahead now and then give find the closed form for this sequence. Cool. Yeah, it looks like a lot of good answers in chat there. Yeah, so the closed form, a lot of people said a sub n was equal to 3n. And yeah, that's perfect. One way we could kind of figure that out is we just take each of these and then we just look at, because we want to find the closed form, we want to somehow relate this to the position of the number. So we've got these in position. This is 1, 2, 3, 4, 5, 6. So we're kind of looking for relations between the position and the value. And so here we could see that, yeah, you just multiply by 3. And then looks like, yes. So yeah, what Daniel Andrew said, yeah, we always are going to start with n is equal to 1 just for our first value. And that's just the standard that the textbook uses. If you look at other textbooks, sometimes you'll find that they do start with n is equal to 0. So just be careful if you're looking at other resources, because sometimes they'll start with n is equal to 0. But for this class, we're just starting with n is equal to 1. Yeah, and then so for the recursive formula, so we've got this as our closed form with that a sub n is. And then someone want to give what would be the recursive formula? So yeah, it looks like some good answers in chat. Yeah, so they're all pretty close, but they're missing something. Yeah, Cameron, got it. Yeah, we need that starting condition. So whenever we want recursive formulas, we have to have some starting value. So for the recursive formula, we need to know that a sub what the starting point is. And so yeah, our starting position here is 3. And then we can do what a sub n is. And it looks like everybody pretty much agreed. So yeah, a sub n minus 1 plus 3. Yeah, if we don't have that starting condition, then whenever we try to use the a sub n is equal to a sub n minus 1, you're just going to go forever, because you're always going to be looking, well, what's a sub n minus 1? And you're never going to have a stopping point. So this is kind of like our end condition here with the a sub 1.
James, there's a question from the chat.
Okay. Oh, so Andrew, is there a general formula for geometric sequences? Yes. Yes, there is. There are general forms for both geometric and arithmetic sequences. Yeah, so here we're actually have an arithmetic sequence. If you remember kind of back from your calculus days, you should have gone over kind of what geometric and arithmetic sequences are. And so here it's arithmetic because we're just adding some constant value every single time. And so arithmetics always, arithmetic sequences always just look of this form. So for an arithmetic sequence, the general form is you would have some a sub n is equal to some constant, let's call it like C1 a sub n minus 1, plus some other constant like C2. And that's always going to kind of be the general form for arithmetic. And then geometric sequences also have a similar form. So if we had like a sequence, just for example, for geometric, if we had like the sequence like 2, 4, 8, 16, 32, etc. So this is a geometric sequence because we can kind of see it's going up by some powers here, and that tells us that it's geometric. And so geometrics are of the form, it's like a sub n is C1 times some constant value. I think they call it like R to the n plus C2 or something. But yeah, if you wanted to work on them yourself, yeah, with any sequence, there's closed forms for their arithmetic and geometric if you can figure out that your sequence is of that type. So yeah, good question. Good question there. Any other questions on this? Okay, one thing I guess I'll kind of go over. So I think for a lot For this problem, it's a little bit easier to kind of find the recursive formula for this problem, just because it's a pretty simple sequence, 3, 6, 9, 12. But what I want to show is that there's actually a way that you can just kind of always find what these recursive formulas are. So let me just get a blank page. And I can kind of explain how we find those. So in general, if we know what the closed form is, so we knew that the closed form was a sub n is equal to 3n, then we can oftentimes easily come up with the recursive form. So to find the recursive form, we're looking for a sub n to be, a sub n minus 1, and then we're looking for whatever these values are. So one way to do that is, well, we know if we start with the closed form, then we can find the n minus 1th term by just plugging in n minus 1 for n here. So you'd have a sub n minus 1 is just 3 times n minus 1. And then if we just simplify this expression, you get a sub n minus 1 is equal to 3n minus 3. And then you'll notice we know what 3n is. 3 sub n is just a sub n. So you can plug in that value here and get a sub n minus 1 is equal to a sub n minus 3. And here we're just plugging in a sub n is equal to 3n. And then we can solve for a sub n and do a sub n is equal to a sub n minus 1 plus 3. And that's the result that you all put in chat. But this may be a more systematic way if you have a harder sequence that you can't quite come up with the recursive formula just by looking at it. And you want a more systematic approach, this might be a way to be a bit more systematic about how you find those recursive formulas. Any questions there? So Parker, does that work all the time? For most sequences, yeah, I think there's a couple. There was a discussion on Piazza about this, where if you're given a closed form of any sequence, can you necessarily find the recursive formula? And so, yeah, it working all the time, not quite sure it'll work all the time. But in this class, most of the problems you're going to work with, yeah, this is going to work. There's just some weird edge cases with the sequences. Cool. So let's go ahead. Didn't see any more questions. We'll go ahead to the second problem. So here we've got this logic problem. So we've got these 3 people, A, B, and C. And then we've got some variables to represent statements. So we've got P represents that statement that A is truthful. We've got the statement Q that represents B is truthful. And then we've got the statement R that represents that C is being truthful. And then we want to basically use our symbolic logic that we know to convert all of these statements. So just as a quick review, when we mean symbolic logic, what we're talking about here is, and is in our symbolic notation, we've got this kind of upside down V. We've got our or is just this V symbol. And then we've got our negation is this symbol. So we want to use these symbols along with these variables P, Q, and R to come up with some equation basically to describe each of these statements. So if you want to go ahead and just take a minute or two on just part A, and convert the statement that A is lying and B or C is truthful into symbolic logic. And then, so does somebody want to volunteer to explain kind of what they got for part A? You're then in the chat or raising your hand. So it looks like we've got a couple different in chat. So we had, so yeah, I think you meant, yeah, the not P. So for part A, we've got some with not P and Q or R. And then we've also got someone with, oh, they changed. Okay, yeah. So not P and Q or R seems to be the general consensus here. And so you can kind of explain why does this not P and Q or R represent kind of this sentence here? Well, we know that P represents the statement that A is truthful. So when we negate P, not P, that's really the same as saying that A is lying. Because we're saying that it's not true, not the case that A is telling the truth. So A must be lying whenever we negate these variables. So we've got A is lying and B or C is truthful. And we see that if we have Q or R, Q represents the statement B is truthful, R represents the statement C is truthful. So Q or R represents the statement B is truthful or C is truthful. And that's the same way as saying that B or C is truthful. The only thing to be careful about here is just making sure that we know where our parentheses are going. So if you have, we want to know that there's kind of this grouping here, that we've kind of got the statement that B or C is truthful is kind of its own statement. So we want to make sure that we remember that when we're converting these to logic, that these parentheses matter. So it would not be the case, not the same as if we had not P and Q or R. Those two equations, not the same thing. You can get different results. If you worked out the truth table for both of these, they wouldn't agree in every spot. So we got to make sure that we remember those parentheses, just because they're really important to kind of encapsulate what we exactly mean. So any questions on this part A1? So it looks like, okay, so we've got a question. Yeah, there is an order of operations. So if you read the book, I believe the order of operations, we've got negation, the way that the book defines it is negation has precedence over everything, then and then or. Yeah, but parentheses definitely, especially for this problem, make a difference. So if you had omitted the parentheses in this case, the and would have precedence. And so you would have ended up with this statement here. Really, because if you would have dropped the parentheses, then we would have got the same thing. So yeah, I would often make sure you just use the parentheses, especially because there's some textbooks as well that consider or and to be at the same level of precedence. So if you look at some other textbooks, they're all off. Some of the other textbooks out there put these at the same level in the order of operations, similar to how like we have like plus and minus are kind of at the same level. So if you're just looking at other textbooks, just make a note of that. So parentheses often just make it easier to kind of explain what you're doing. But yeah, there is order of operations too. Cool. So let's go ahead and we'll do the second part B. So go ahead and do, yeah, A and B are lying, or A and C are truthful. And then, yeah, if you just want to go ahead and throw your answer in the chat, and we'll kind of take a look. So we've got one, we've got not P and Q or P and R. Then we got another not P and not Q or P and R. It looks like that's kind of we've got those two answers there. And then, yeah, does it matter if the negation is outside the bracket? Yes, and we're going to go over that. So these two answers here, these do not represent the same thing. And the reason that they don't is, well, we can kind of look at it. First, we'll look at it just logically and kind of break it down. And then we'll kind of explain. So the first part here, what we're really saying in this part is not P and Q. So remember that P is the statement A is truthful, and Q represents statement B is truthful. So not P, or not P and Q, that represents the statement it's not true, not the case, that A and B are truthful. And that's not P and not Q here. That's kind of represents the statement that it's not the case that A is truthful and it's not the case that B is truthful. Or it's really A is lying and B is lying. And these two things mean slightly different. In the first case, we're saying it's not the case that A and B are truthful, or it's the case that at least one of them is lying. So it could be the case that A is lying or B is lying, or they both are. But this just means that one of them, at least one of them, is lying. Whereas this case, the second one, not P and not Q, means that they both are lying. A is lying and B is lying. And the other way to kind of think about this is just from De Morgan. So if we use De Morgan's law, using De Morgan, we have not P and Q is not P or not Q. Remember, with De Morgan, we can distribute the negation as long as we flip the and to an or here. And this is not the same as what we said before. So yeah, so this, for part B, this is the statement that we really want. This is the correct one. And it's just because of, yeah, just making sure that that not is actually distributed to both the P and the Q, because we want A to be lying and B is lying. So it's a little tricky there, especially with the when it's kind of written out as a sentence, but just make sure of that. And yeah, it looks like chat kind of said the same thing. Yeah, difference because of De Morgan, right? Yes.
So if students answers not P or not Q is also right.
If not P
Or not Q.
not Q. Oh, yeah, so the negation outside, yes. So it would also, let me go to another slide. So yeah, so we had not P and not Q, or P and R. And then someone else is saying, can we do not P or Q? Can we do this one? And the answer is yes, we can. They're actually, these are this is the same. Logically, they're the same. And we can kind of see that using De Morgan, we can show that these two statements are equivalent. If we use De Morgan on this bottom statement, then this is equivalent to, we can distribute that negation as long as we flip to an and, not P and not Q, or P and R by De Morgan. So yeah, that would also, this would also be a correct answer. Any other questions for part B? Looks good. Cool. So let's go ahead and finish this problem up. So C, we had, we need to represent at least two people. Are telling the truth. And just out of the interest of time, I'll just kind of go through how we would solve this one. Or actually, no, we're done at 2:50. Yeah, so you can just take a minute and go over this one. And then if you just want to type in chat or raise your hand and we'll go over it. And yeah, it looks like we've got a couple in chat. Yeah, everybody seems to be agreeing. Yeah, so we can do P and Q or P and R or Q and R. And yeah, that seems to be what, yeah, everybody's agreeing on. And the reason this one works is because what we're doing here is we're just really just checking that two people are telling the truth. So this first statement, this is checking if A and B are truthful. Here we're checking if A and C are truthful. And then here we're going to check if B and C are truthful. And since we checked every possible combination of two people, then we know that at least two people are telling the truth. Now, it could also be the case that all three are telling the truth. And that's going to be fine too, because all of these statements are just going to evaluate to true. P and Q would be true, P and R would be true, and Q and R would be true if A, B, and C are truthful. And so this would evaluate to be what we want. So yeah, it looks like everybody kind of agreed there. Anybody have any questions on this one, part C, or had something different? No, looks good. So then the last part, the last problem we have is just we want to represent that exactly two people are telling the truth. So how could we do this case? If you just want to type in chat or raise your hand. Okay, looks like we've got some good answers coming in chat. So one, we've got this P and Q and not R, or P and R and not Q, or Q and R and not P. And then we've got some others saying we could append a statement to the last part. So this is kind of one idea. Second idea is to have what we had before, P and Q, or P and R, or Q and R, or not P and Q and R.
I think it's and not P.
Oh, and yes. Or and not P.
And not P and Q. The or be the or just behind.
Oh.
And R should be and.
Which or?
The final or should change to the end.
Oh, yes. Yeah, I didn't copy theirs down. Yeah. Yeah, the or and that.
Yeah, and I also need.
Would parentheses be needed around part C?
It means the three or should be in one parenthesis.
Oh, do we need this?
Yes.
Yeah, that would definitely be good to, yeah. Yes, we do. Yeah, good catch. We do need all of those in parentheses. Just because of that and precedence would group the two statements on the right together, and we don't want that. So yeah, it looks like though was kind of the consensus in chat for these two. And these are both correct. So both of these statements, logically equivalent statements, both are fine for answering this question. And the reason why is, so if you look at this first idea, what we're doing here with P and Q and not R is we're checking that A is telling the truth and B is telling the truth and C is lying. And then for the second part, we're going to check that A and C are telling the truth and B is lying. And the third part here, we're checking that B and C are telling the truth and A is lying. So what the kind of idea here is we took what we did in part C and just made sure that we checked only two people were telling the truth in each case. So we just add the statement checking that the other one is lying each step of the way for the first one. And then the second solution that people had come up with is to take what we did in C, basically, that either A and B are telling the truth, or B and C are telling the truth, or A and C are telling the truth, and then just check, and it's not the case that all three are telling the truth. And that also works to show that only exactly two people are telling the truth. So both these are logically equivalent. So anyone have any questions on this part? So Jonathan, on the previous one, there's an implied extra pair of parentheses, right? Something like P and Q or P and R or Q and R. Like in Java, you'd have to group one pair together. Does that apply here as well? On part C. It actually, you don't actually have to group them. Because with these ORs, we have associativity properties. So you don't have to, but you could if you want to. Perfectly fine to group any one of these OR statements if you wanted to do that. You could group them as well, but we don't have to for this one just because they're all ORs, and we have those associative laws. We can group any ORs together in parentheses. Similar, we have associative properties if they're all ANDs. Cool, yeah. Any other questions before we go? How is participation being recorded? We don't record participation for discussions. Yeah, it's just kind of the expectation you come to get extra practice on the homeworks and stuff. And you'll notice if you look at the homework, some of these problems that we just did will look pretty similar, if not identical to some of the problems. So that's some of the benefits of coming discussion. And then I guess last question, is there any other type of notion that we should be aware of? What do you mean by that? You just unmute yourself. Or notation? Yeah, what do you mean by other notation? Logical operators? Yeah, actually, so if you watch the next lectures over 1.3 and the next two lectures, you'll actually see we'll get into implication. And that'll be the other logical operator that you'll need to know. And yeah, they are right. Yeah, like in Java, those two. Once we start submitting homework assignments, we'll be reviewing the answers during the discussion sections. No, not for homework, I believe. If you have homework questions, you just come to the T office hours. But we will go over some of the quiz questions, I believe. Cool. So we're done for this session. We'll have quiz homework during the quiz week. Yes, I do believe some of the homework's lined up that way. So yeah, but thanks everyone for participating.